Hello dear student, welcome again in my YouTube channel. Yesterday I have told you some problems related to the equivalent weight, how it depends upon the reaction and how it is calculated. You have seen in my previous lecture. Calculation of equivalent is very important in the chemistry numerical because all the reaction depends upon the gram equivalent reacted equal to the gram equivalent of product form. So for calculation of gram equivalent, you must know the equivalent weight. So in the same series, today I will take gas as a material. So before gas or gases, you should know the ideal equation of gases, how it depends upon the pressure, temperature and volume. So we start from the ideal gas equation. I don't discuss more about the Boyle's law, Chor's law. I think you have already studied or known in your previous section. So I just start from the ideal gas equation, PV equal to nRT for any gas, for all gases follow the ideal gas equation. The ideal gas equation PV equal to nRT. Suppose this is a container, closed container or closed vessel or closed system. This is a closed system. Suppose N is the number mole of any gas, N is the number of moles of gas in the vessel, and P is the pressure of this vessel, T is the temperature of the gas, and V is the inside volume of the vessel, volume of the vessel. So here these are the conditions under which n moles of the gas are present in a closed system. One thing you must know, 1 or 2 mole or any mole placed in a vessel, it occupies full volume. The density of gas is converted or differ, but the volume of the container is the volume of gas. So this is PV equal to nRT. Here P is the pressure of the gas or of the vessel, you can say of the system in atmosphere. Unit must be known, atmosphere. V is the volume of the gas occupied, volume of the gas occupied is the volume of the vessel, or you can say volume of the vessel, Take in liters. We take it in liter in chemistry. These are the units which are frequently used, and I will also explain these numericals in atmosphere, liter, and temperature, T, temperature of the gas in Kelvin or absolute. This is absolute temperature, absolute. So temperature of the gas, and N is the number of molecules of the gas present in the vessel. in the vessel. And R is the gas constant. R, gas constant. Value of this gas constant is 0.0821. Value will be atmosphere liter per k mole. This is the unit of the gas constant. So you just start from the ideal gas equation. All the gases follow this rule. Pressure into volume of the gas equal to number of mole into gas constant into temperature in absolute. So if more than one gases are present here, so in this case what will be happen? I will discuss here. This reaction can be generalized in so many forms. This is one. I think you note down all these things, and you know here, you know number of mole, weight of the gas, say W divided by molecular weight of the gas, that is capital M. So put N equal to W by M. So PV equal to number of moles, you put weight by molecular weight, R into T. Then take mass here, volume here, so P into M equal to weight by volume, RT. And weight by volume for any case is the density of the gas. So pressure into molecular weight equal to dRT. So M is molecular weight of the gas, and D density of the gas. So many times this equation directly used. And similarly, you know, I have told you earlier, vapor density equal to molecular weight by 2, that is molar mass with respect to hydrogen. So M equal to 2 of vapor density Vd. So put here M, P into 2 Vd equal to dRT. So for any gas, if pressure is temperature is constant, then vapor density directly proportional to the density if pressure and temperature constant. So many places this relation is directly used. So you must know Pm equal to dRT. It is also a form of ideal gas equation. PV बराबर nRT is the original gas of equation. Now we discuss one problem so you can understand better. Suppose in this container 5 gram of hydrogen is placed. Suppose in question, this is a container, 5 gram hydrogen put at 0 degree centigrade, and volume of the container is 500 ml, and temperature already given. Then find the pressure of the gas. So suppose this is the question first. This is a closed vessel. 5 gram of hydrogen put here at 0 degree centigrade. Volume of the container is 500 ml. Find the pressure of the gas. So let us see what is given here. Volume of the gas volume of the gas 500 ml, convert into liters, that is 500 divided by 1000, because in this equation we take the volume in liter. So 0.5 liter, this is the volume. And temperature of the gas 0 degree centigrade, that is 273 K. 0 degree, you can convert it 0 degree to Kelvin. So K equal to 273 plus C, degree in temperature. You can convert in Kelvin. Now two things are given, volume and temperature. Now what is the weight? Weight is given, weight of hydrogen gas 5 gram. You can calculate the molecular weight of hydrogen. Molecular weight of hydrogen 1 into 2. So you have to find out the pressure. Just I have told you earlier, P into M equal to dRT, or say weight by volume RT, just inverse, this will come. So P into V equal to weight by molecular weight RT. The same number of moles, weight by molecular weight. So you have to find out the pressure. Let pressure is P, volume is 0.5, weight is 5 gram, molecular weight 2, value of R is 0.0821, and temperature 273. So simplify this pressure equal to, you can simplify. So I think 5041.41 into 273, that is like something. This is the value in atmosphere. So you have simplified the value of pressure in atmosphere, you can calculate easily. So this is the first example. Similarly, I will tell you one more law, that is Dalton law. Dalton law, which is very important for the numerical point of view. You have read it in your 9th, 10th class. Dalton law. What Dalton says? Dalton says, number first postulates is atom is the basic unit of the compound or element, which participate in the reaction. First postulate. Later it was proved that atom is further divisible. He said atom is indivisible. He also said atom is indivisible. And number third, suppose if more than one gases are placed in a container, the total pressure of the gases will be the sum of partial pressure of the gases. So it is very important for numerical point of view. Dalton says, suppose this is the container. Here more than one gases are present. Suppose oxygen, nitrogen, hydrogen, these gases are present. So NO2 number of moles of oxygen, NN2 is the number of moles of hydrogen, NH2 hydrogen. So these are the number of moles present, and P is the total pressure, V of the volume of the vessel, and T is the temperature. So if one gas, this gas, oxygen gas, alone put in the same vessel, suppose this is the vessels of same volume and temperature same, and oxygen is put in this vessel of NO2 molecule, NO2 mole. So the pressure is called PO2, that is pressure exerted by the oxygen only. So this is the partial pressure of oxygen in this vessel. It means the partial pressure is the pressure which is developed only due to oxygen molecules. So how will it calculate? If we put this molecule in a separate vessel of same volume and temperature, same number of moles, the pressure exerted by these oxygen moles or oxygen is the partial pressure of oxygen. Suppose PO2 the partial pressure of oxygen. Similarly, PN2 is the partial pressure of nitrogen, and PH2 is the partial pressure of hydrogen. Then total pressure of the vessel will be P partial pressure of oxygen plus partial pressure of nitrogen plus partial pressure of hydrogen. This is the total pressure. This is the Dalton law. Total pressure. Now we take one example. Suppose this is a container, contains hydrogen gas 4 gram, oxygen 16 gram, nitrogen 0.5 gram, and the volume of this container is 5 liter, temperature 273 K. So you have to find out the partial pressure of hydrogen, partial pressure of oxygen, and partial pressure of nitrogen if 4 gram hydrogen, 16 gram oxygen, and 0.5 moles of nitrogen are given. So how will you calculate? Suppose P is the total pressure of the system. So you have understood what is the partial pressure. Partial pressure is the pressure of the gas exerted by the only one component of that gas is the partial pressure. So suppose PH2 is the partial pressure of hydrogen, PO2 is the partial pressure of oxygen, PN2 is the partial pressure of nitrogen. So we have to calculate the value of these partial pressure, hydrogen, oxygen and nitrogen, and total pressure. So we know ideal gas equation PV बराबर nRT. So for hydrogen gas, suppose pH is the partial pressure is the pressure exerted by the hydrogen only in the vessel. So P partial pressure hydrogen volume 5 liter, 4 gram, 4 by molecular weight, weight by molecular weight, that is 2 moles. Moles or gram mole, both are the same thing. So value of moles 2, R into temperature. So PS2 will be 2 into 0.0821 into 10 power 23 by 5. Simplify it, you will get the partial pressure of hydrogen. Similarly, partial pressure of oxygen, if we calculate, calculate the 16 gram into moles, so 16 by 32. 32 is the molecular weight of oxygen. So PO2, partial pressure of oxygen into volume. All the gases will occupy whole volume, that is 5 moles R and T. So partial pressure of oxygen, put the value of R and you will get, simplified, you will get the partial pressure of oxygen. Similarly, for nitrogen, 0.5 mole direct is given, so put the value of 0.51, Pn2 into 5 equal to 0.5 into R into 273, then Pn2 will be 0.5 into 0.082 into 273 divided by 5. So simplified, you will find first partial pressure of all these, partial pressure of hydrogen, oxygen and iron, you will simplify. Now we see total pressure, also find the total pressure. So total pressure is the partial pressure of hydrogen plus partial pressure of oxygen plus partial pressure of nitrogen. So if you sum up this, you will get here total pressure. But if we see these three partial pressure equations, if we summarize, then 5 take common, PS2 plus PO2 plus PN2 equal to RT take common, this mole plus this mole plus this mole. Or we can say in other words, this is the total pressure, sum of partial pressure into volume, sum of gram moles into RT. So here this is the total pressure. So if you have to calculate the total pressure, no need to calculate the partial pressure. Just PV equal to number of moles total, N1, N2, N3. This means total pressure exerted by all the moles of all gases. This is the sum up into RT, you will get the total pressure. So partial pressure, if you have to calculate, you calculate separately. If total pressure calculate, then either you sum up all the partial pressure, you will get, this is the Dalton's law, or from here you see P is the total pressure. If more than, write down, if more than one gases are present, so pressure into volume equal to sum of N, total number of moles into RT. This is the important question. If the moles of more than one gases are present. So this is the Dalton law of partial pressure. I will give you some more example. Here I will give you one law which is very important in chemistry in numerical point of view, that is Graham's law of diffusion. Graham's law of diffusion. You all have heard this name and this is very common. Graham's law says rate of diffusion of any gas is directly proportional to, inversely proportional to square root of density. Sorry. Graham's law. Graham's law says कि rate of diffusion of any gas, rate of diffusion is inversely proportional to square root of density of the gas. So this is the basic law of Graham's. So what is the rate of diffusion? Rate of diffusion you can understand better. rate of diffusion, if we can rate of diffusion, suppose this is a container, contains 5 moles. If there is one hole, so the gas will diffuse out. So how much gas is diffused or came out, the quantity is the diffusion rate, means per unit time. So it depends upon the density. Suppose here oxygen or hydrogen, there are two gases. Two gases. Suppose this is N1, this is N2. Number of mole is N1, number of mole of S2. So rate of diffusion is the volume of gas diffused divided by time taken. How much time it takes to diffuse. Suppose N1 में if it is diffused A moles in 5 minutes या in T time, so rate of diffusion will be for hydrogen, rate of diffusion of hydrogen will be A by T. A moles of hydrogen will diffuse in T times, the rate of hydrogen will be A by T. So you must understood this thing. And second thing is very important. Similarly for oxygen, if B moles, suppose B moles in same time T, the rate of diffusion of oxygen will be B by T. And this is directly inversely proportional to square root of density of hydrogen, and this is proportional to inverse of density of oxygen. If we summarize, so the equation will be rate of hydrogen, rate of diffusion of oxygen equal to, this will go up, square root of density of oxygen upon density of hydrogen. So this is very important. You can note here. And if number of moles are diffused per unit time is given, so rate here will be T cut हो जाएगा. It will be rate is directly proportional to the amount. So A by B. A moles of hydrogen, B moles of oxygen equal to inverse square root of density. So this is the one equation, very important. Next, I have told you earlier, in gas equation, you note down, in gas equation, Pm equal to dRT. It is also a form of gas. I have told you earlier. And molecular weight by 2 is the vapor density. So vapor density equal to 2 into molecular weight, put here. So P into 2 vapor density equal to dRT. If pressure and temperature is constant, if pressure and temperature is constant, if hydrogen or oxygen or any two gases in the same vessel, it means temperature and pressure are same for both. So vapor density is directly proportional to the density of the gas. Vapor density, you know what is vapor density? I have told you earlier, you remembered it. Molar mass of a gas with respect to hydrogen gas. Molar mass, that is molecular weight, and molecular weight of by 2, this is molecular weight of 2. This is the definition. So you must remember, the vapor density is the molar mass of gas with respect to hydrogen gas. So vapor density is directly proportional to D, put here. So you will get R1, if we generalize the equation, R1 by R2 equal to square root of D2 by D1 equal to square root of vapor density of 2 divided by vapor density of 1 equal to square root. Vapor density is directly proportional to molecular weight, so it is M2 by M1. So you have to remember all these relations. These will be applied in anywhere. Rate of diffusion is inversely proportional to square root of density, and we have seen the relation of density with vapor density and molecular weight. So rate of diffusion is also the inversely proportional to the molecular weight. So let us take one example. I think you understood. You have already seen this type of problems in your previous 10th, 11th level, but there is a application of these laws. Here you see in medical and engineering, there are frequently questions asked from this chapter. So let us find out. In a closed vessel, 10 gram oxygen and 14 gram nitrogen are placed in a closed vessel present. There is one hole in the vessel. The rate of diffusion, find the rate of diffusion of nitrogen gas if 1 mole of oxygen released in 10 minutes from the pinhole of the vessel. Here, rate of diffusion of nitrogen. You have found the rate of diffusion of nitrogen. In a container, 10 gram of oxygen and 40 gram of nitrogen are placed. Find the rate of diffusion of nitrogen if 1 mole of oxygen released in 10 minutes from a pinhole. In some cases, rate of diffusion of oxygen is given, then find the nitrogen. But here, quantity is given, 1 mole itne, so how many moles in it? So let us see. Suppose R and 2 is the rate of diffusion of nitrogen gas and RO2 is the rate of diffusion of oxygen gas. So we know Rn2 divided by RO2 equal to square root of density molecular weight of oxygen divided by molecular weight of nitrogen from the previous. And rate of oxygen, if we find out rate of, we know the molecular weight of oxygen. Molecular weight of oxygen is 32. And molecular weight of nitrogen is 28. So here just weight is given for the confusion. There is no role of this weight. The information completely given here. This 10 gram, 14 gram is only a confusing figure. So we know this value, we have to find out the rate of this. So if we calculate the rate of oxygen, rate of diffusion of oxygen. So here you find out rate of diffusion of oxygen means what moles of O2 released, or may be taken gram of oxygen released, or partial pressure dropped, all are the same thing, or partial pressure drop divided by time taken. Rate, it is rate. Rate means in what time. So here we see 1 mole in 10 minutes. 1 mole 10 minutes convert into second. So 10 minutes. You may also write in minutes. So answer of this will be in minutes. So 10 equal to 0.1 moles per minute. So this is the rate of oxygen. So put here. So R and to rate of nitrogen equal to rate of this side, rate of oxygen into square root of molecular weight of oxygen 32 divided by 28. And rate is given 0.1, and this will be the square root of 1, and then 40, then 1, and 12, 4, you can say 4. So if we simplify 0.1 into 1.28 approximately, so this will be 0.128. This is approximately value. Approximate, calculate the exact value. So this is the rate of diffusion of nitrogen per mole per minute. Unit will be same, moles per minute. So this is very important question in CPMT, NEET, JEE Advanced, such type of question frequently asked. So practice more and more question. We will take one more question here. If the rate is given in the terms of distance travelled per unit time, rate of the diffusion is also defined. So note down, the rate of the gas diffused is also defined in the terms of length travelled per unit time. So here rate of diffusion is also defined as the distance travel per unit time. Let us see through an example. Suppose there is a long tube. Tube is 1 meter long, that is 1000 mm. From here nitrogen gas is released, and from here hydrogen gas is released. The question is, at what distance from the nitrogen these will meet and form ammonia? Suppose it form ammonia. Suppose actually ammonia is formed under the certain conditions, pressure and temperature. You have seen in the Haber process, very high pressure, very high temperature, but it is assumed ammonia is formed here. So you have find out the times taken to form the ammonia. So the question is, find the distance from the nitrogen side, to form ammonia. So let us see what happened. आपको ये बताना है कि from one side nitrogen gas is released, this side nitrogen gas released, from this side hydrogen gas released inside the tube. This will come, suppose meet here, meet at the point P. Suppose point is K. No, A, P cannot, we take the point A. And this is the tube of length 1 meter. So, you have to find out this distance. Suppose nitrogen and hydrogen will meet at A point and distance is dx. So, how will you see? How we calculate it? This question is asked so many times in various exams. So we see, let hydrogen and nitrogen gases will meet at point A. Both will meet at point A and form NH3. The distance of point A from nitrogen side is x. This is the distance x. And time taken to meet at point A is T. So T time, same time both the gases are released. This side nitrogen, this side same time. Here one thing must be noted, same time both the gases are released same time, and it will take T time to meet at point A. So distance, this is x, so this distance will be, this is 1000 mm, that is 1000 minus x, this is the distance, and time, both travel time will be same because this will meet same time. So this time is taken T here, T time from here, and this will T time from here. So rate of diffusion of nitrogen, you find out distance traveled divided by the time. Distance, this is the rate of diffusion. Which gas travel more distance is more fastly diffused. So distance travel, as I have told you earlier, this is distance travel per unit time. So distance traveled by nitrogen divided by time taken, and time will be same for both because at the same time these are released, so mix at the same point. So distance is x and time is t, x by t. Similarly, rate of diffusion of hydrogen equal to distance traveled 1000 minus x divided by t. Time is taken t. This is the rate of diffusion in the terms of distance traveled per unit time for both the gases. Now we